Okay. So last time we left off talking about functions in 2.1. We talked about a couple different things about functions. We talked first about what a function was and how to determine whether a relation that defined a set of ordered pairs was a function. Let me share my notes here. Here we go. All right, so we started out by talking about finding the domain and range for a set of ordered pairs, which was a relation. Then we talked about whether or not the relation was a function. We said that it was not in this case because we had two values that were repeating in the domain. Remember, it's okay if your range values repeat, but your values in the domain cannot repeat. Otherwise, you're violating the definition of a function where the domain corresponds to exactly one element in the range. All right, we talked about how to determine whether an equation represented a function. We looked at two examples there where one of them did and the other one did not. We talked about special function notation that's read f of x or f at x. We talked about evaluating functions first. By the way, we're going to do some more of this today. But first, we looked at just evaluating a function at a specific integer value. Then we looked at evaluating a function at an algebraic expression. In our case, it was f of x minus 1. So you should have, if you got through the homework already, which I'm sure maybe half of you did. There's not a lot of time between Monday and Wednesday, but you should have seen some of these on your homework where you had to evaluate functions at algebraic expressions. Nothing too crazy, but you'll probably see some binomials here and there. We did a pretty standard word problem, and then we ended up graphing some functions by plotting points. That's not something we're going to be doing a ton of in this chapter. We're going to be doing a lot more point plotting later on in chapter 3 to come up with missing pieces on our graphs. But yeah. If for something like number 7 where it's linear, if you already feel pretty comfortable with using y equals mx plus b and using the point and the slope to graph it, that's fine. You don't have to include a table of values in that case. But for something like an absolute value, that's somewhere where I'd probably ask you to make a table of values, and I would ask you for a specific number of points just to verify that you had the right shape. So this absolute value graph was the V shape. Oh yes, and then at the end we talked about the vertical line test to determine whether or not your graph represented a function. So something like number 9 looked like a parabola, and we said that it was a function because we wouldn't be able to draw a vertical line through the graph that would hit the graph more than one time. And each place the vertical line only hit the graph once. That was not the case for something like number 10, where I drew a circle, and it's very easy in that case to find a spot where if you drew a vertical line through, you'd hit the graph more than once. Something like this function, even though you technically don't violate it over here, remember that you're looking for something like this type of behavior to occur. All right, that is what we talked about last time. Now, we're moving on. Before I do that, does anyone have any questions about the information that I just recapped for you from last time? Okay. Daniel looks just like one of my friend's husbands, and every time I see him, I'm like, oh, I know that guy. And now I'm just going to know this person as Daniel, and then maybe it'll reverse. Sorry, Daniel. Please do keep your screen on, though, okay? It's nice to see the pictures, even if I have something awkward to say about them. All right, let's see what's happening here. Okay. Get my thingy up here. We're going to identify information about a function from its graph. And then we're going to look at a graph and determine the domain and range of the function and find intercepts and do all sorts of things by looking at a graph. All right, so to find the domain of a function from its graph, we're going to look for inputs on the x-axis that correspond to points on the graph. Some of this I think doing it is easier than actually reading the definition. The definition makes it seem like it's something worse than it is. I think this is pretty straightforward when we get into it. For the range, we're going to look at outputs on the y-axis that correspond to points on the graph. The graph of a function f is given. Let's see. Use the graph to answer the questions. So you might need to, if it's helpful to you to fill in some of these blanks, feel free to do so, because we're going to be interpreting some information based off this graph. One of the things that I will fill in here for you, which I meant to do and then forgot to do, was this point over here. It's not very clear where this point is sitting, but it's supposed to technically be sitting here. And if you're not sure what that is, well, if this one's 20, we have 1, 2, 3, 4, 5 tick marks. So it must be the case that these go by 4s. So if it helps you to label these all the way, I should make a note to change this for next semester to just label all of these. Maybe I didn't because it was a spacing issue. Maybe it's good for us to label them together, but that's fine. Same idea here. We have 20 and then 1, 2, 3, 4. That's our 5th tick mark. So we can go ahead and also count down from 20 this direction. 16, 12, 8, and 4. And we can do that as we head down. And then to the left. -4, -8, -12, -16. And then you can just assume that right here the graph is crossing directly in between 12 and 16 for when we get to that. Is there anything else that's missing? I don't think so. Okay. Use the graph of f given below to answer the following questions. A, find f of 16. What this means is, and I'm going to rewrite this using the English language in case you find that helpful. What this means is when x equals 16, find y. You will get used to using this terminology. Until then, if you want to look back to these translations that I'm going to write down, feel free to do so. You're either going to be going one direction or the other. Either here's x, find y, or the opposite direction of here's y, find x. So if x is 16, we're looking for the value of y on the graph. So you are going to go to 16 on the x-axis, which is right here. And then wherever the graph is, that's where you're going to look. So in our case, when we're at x equals 16, we're going to go up to get to the point on the graph that corresponds to x equals 16. So when we are at x equals 16, the corresponding y value is 8. So we can say y equals 8, and that means, that means that f of 16 equals 8. All right, questions so far? Okay. Some of you probably have more experience than others with reading this function notation and looking at these graphs. And for some of you, it might have been a while. So, so bear with me. All right, now B is for what numbers x is f of x less than 0? And again, when you see f of x, you should be thinking y. F of x and y are synonymous as long as you're looking at a function. So you're talking about the case that y is less than 0. Now, y is less than 0 for anything that's graphed below the x-axis. So this occurs below the x-axis. So when you're thinking about values of y, you know that the values of y are positive starting from the origin and moving up from the x-axis. And the values of y are going to be negative as you work your way down. So what we're looking for are the numbers x for which this graph has a negative value for y. So ignore any parts of the graph that are on top of the x-axis. So for instance, this whole part over here, as the graph goes up and then back down again, all of these y values are positive. We're trying to find values of x for which the value of y is negative. The values of y start becoming negative as soon as we move past x equals negative 12. So x equals negative 12 is that point where now we're sitting at y equals 0. As soon as we move beyond that, that's when the values start to become negative. Now we're going to write this in two different ways. The first one will be set builder notation. Your book kind of works back and forth between two different types of notation. Set builder notation is used not quite as often, but it's used a little bit more in this chapter. Interval notation is going to be used a lot throughout the rest of the course, so I'm going to make sure that we talk about both of these so that you know what to do in both instances. All right, so we're going to set up the set builder notation. Oh, whoops, sorry, I put that on C. Yikes. Wrong place to put that. Okay. Clearly, I should have left a little bit more space there. Sorry about that. All right, so we are looking for values of x. So for what numbers x is the value of y less than 0? The values of x are going to start out with x equals negative 12. And notice that as you move to the right from negative 12, the values of y are still below the x-axis. So the values of y are still negative until we get to this point right here. And as soon as we get to x equals 14, now the y value is 0. And as we move to the right of 14, the y value becomes positive. So we're going to take our value of x all the way from negative 12 to positive 14. And any value of x in between those two numbers will have a negative value for the corresponding y component on the graph. So we're going to start out at x being negative 12. And then when we build our set builder notation here, we can just use some inequalities to represent what's occurring on the graph. So we can say that x has to be between negative 12 and positive 14. Now, I did not use less than or equal to signs, and I think many of you guys know why. If you're not sure why I didn't include the equal to sign, it's because if x is equal to negative 12, the y value is not actually negative, it's 0. Now, if your question would have said for what numbers of x is f of x less than or equal to 0, in that case, we would have included negative 12 and we would have included 14. But because we're talking about values of y that are only negative, we have to include only values in between negative 12 and 14. So we do that by using these strict inequalities. Before I do the interval notation, does anyone have a question about the set builder notation or about why we chose those values of x or why we wrote it the way we did?
I got a question about the set builder notation.
Yes, Ben.
Where'd you get the, or how'd you, I don't know how to say this. I kind of missed the part where you put the bracket thing, then the x, then the line, then negative 12.
Mm-hmm.
Can you just explain that like one more time?
Okay, yeah, so the set builder notation, I know it's just a formality of the notation. It basically is just saying, here's the variable that we're talking about, and then given this variable, here's what follows. So basically you list the variable, then you kind of put a line there. I should make it a little bit longer so it doesn't look like a 1. But
yeah, I kind of thought it was a 1. That's what I was freaking out about.
Yeah, no, it's not a 1. It's like it's just this line that's automatically in the notation.
Okay.
So you always list out what variable you're talking about because it's not always going to be the case that the variable is going to be listed here. It kind of depends on what is in your answer. Like for instance, if we just had one solution, we would have just listed one number. We wouldn't have had a range of numbers, so we wouldn't have used our variable again. Does that answer your question, Ben?
Yeah, that's good.
Okay. I'm glad you asked because I know set builder notation could be strange for some of us, especially if we haven't seen it before. Anyone else question on the set builder notation or the values that we chose to put into the notation? Okay. The other way of writing this is in interval notation, and I want you guys to become really comfortable working back and forth in between the two types of notation. Interval notation is kind of nice because it looks a little bit simpler. There's not quite as much going on with it, and we are going to be using that more often in this class. Interval notation kind of comes directly down from what you did with set builder notation. It's easy to build off of that. If your inequality signs are strictly less than or strictly greater than, but in this case they're strictly less than because our value is in between, we're going to use parentheses. I'm going to say that this is interval notation so it's clear. We're going to use parentheses because we don't have the equal to sign, we just have less than. If you had less than or equal to, we would use a square bracket. And we're going to be using some square brackets in interval notation in a little bit here later on today. So you will see examples of that happening. If it's just strictly less than, use this open parenthesis. And what this is going to do is it's going to include any values that are in between -12 and +14. So we'll include our first value as -12, and then we'll put a comma in between the first and second values in the notation. And then the second value is 14. And then we just close it off with another parenthesis because, again, we have that we can't be equal to 14. Now, you guys probably saw a lot of interval notation when you were doing like number lines and shading and stuff like that. And you might have seen it with well, I guess on the number lines and shading, some people do like open circle versus closed circle, but other textbooks actually use parenthesis versus bracket. And if you did that, then this is going to be a little bit more familiar to you. If not, I find that students tend to latch onto interval notation pretty easily. It's not too big of a learning curve. But this is what we're going to be using most of the time. Your book might go back and forth on the homework. You'll see this one more often. So the interval notation is a little bit simpler. You don't have to include the variable there either. Any questions? Yes, go ahead.
In the homework, they use brackets instead of parentheses. Will you be like taking points off on the quiz or the test if we didn't use like one or the other?
Okay, so on the test, it's a great question. Because it is part of your answer, it is incredibly important that you have the correct notation. So yeah, so technically if you had -12 to 14, but instead of parentheses, you had brackets, the squared off brackets, then yes, that would be built into the rubric, so I would take off some points for that. Depending on the problem, I mean, more of your points are coming from the values that you're finding, but the notation's important too. In my math lab, I don't even think it'll tell you that you have the wrong bracket. I think it might say something like, check your notation or whatnot, but I don't think it's going to tell you that you have a parenthesis instead of a square bracket or vice versa. So yeah, the homework will be worse because you might get the whole thing wrong even though you have one of your brackets wrong. Whereas on the test, at least you'll get, you know, a fair amount of points, but you'll lose a little bit on the notation.
All right, thank you.
You're welcome. Thanks for asking. Any other questions on the interval notation? Okay. So that one's a little bit more abstract than some of the other questions. C is asking for the domain of f and the range of f, and both of these we're going to write in interval notation. So to find the domain of f, we're looking for the values where there is something graphed for x. So when you're thinking domain, you should be thinking left to right. Sorry if that's coming out backwards on your computer. Left to right for the domain. So we're looking at values that are covered on the graph as we move our way from left to right. And we're going to put this in interval notation. So first we're going to start out by looking at the smallest x value for which we have a point graphed. Now, if you want, you can just kind of pick a spot on the graph and move to the left. And as you keep going to the left, you'll notice that the graph stops here. This is the lowest value for x for which this graph is drawn. This happens to be the point that corresponds to x equals -20, y equals 12. And you don't even need the y part, because when we're talking about finding the domain and range, we're just looking for domain at x values, and for the range, we're just looking at y values. So the first x value that's covered is x equals -20. And you won't be able to find anything graphed for any values of x that are less than -20. This is the first point on the graph. There's nothing that exists to the left of this point. So when we start to write this in interval notation, here's where you're going to see a change in the notation, because we actually have a point graphed here. The point actually exists such that x can be equal to the smallest value, -20. So when we put this into our interval notation, for the domain, I'm going to say that the smallest value that I can attain as far as x is concerned is -20. And I'm going to include a squared off bracket in this case, because the point value actually exists at -20. Every once in a while, you might see that you have like an open circle at the end. If this circle were to be clearly open, that means that you approach the point, but you never quite reach it. In that case, you'd have a circle. We will see some examples like that a little bit later today. So you're gonna see a lot of these types of scenarios. For the domain, we found the smallest value that x could possibly be. Now find the largest value. So you're going through your graph all the way to the right. So go to the point that's furthest to the right, and the x value that's furthest to the right on the graph is +20. And there's a closed circle there. The graph actually exists at +20. So the domain covers values of x from -20 to +20. So remember that the domain will be the values of x that are graphed. Any questions on the domain? Okay. Thank you for the visual feedback for those of you who are giving such good visual feedback. All right, so let's talk then about the range. Same idea. This time, instead of looking from left to right, we're going to look from bottom to top. So we're going to find the smallest y value that's being graphed and the largest y value that's being graphed. So yeah, sometimes when we think domain, we think left to right. When we talk about the range, we're going to think bottom to top. So the range will be bottom to top. What are the y values that are being covered? So scan your graph, go all the way to the lowest possible point that's graphed. And it's not this one, it's down here. And I know it kind of looks like this is off to the side of the minimum, but just take this as the smallest y value that occurs on your graph at -16. So now we're looking at the y values. This point corresponds to y equals -16. That is the smallest y value for which this graph exists. So we're going to go ahead and make that the first point in the range. And we're going to use a squared off bracket because this circle is filled in. The point actually exists on the graph. Okay. Heading up to the top, the uppermost point on this graph, if we move all the way up, the largest value for which we have a value graphed, we added a tick mark there at the beginning. We'll call it 24. The largest y value that occurs on the graph is 24. Just make sure that you're kind of doing like a scan of the whole graph, because sometimes students tend to look at values that are close to the axes and then forget to look out at what's happening at the sides. And what's on the side of the graph can have a major effect on your domain or range. So make sure you're looking at the whole thing. All right, so the domain covered values from left to right, the range covered values from bottom to top. Any questions on the range? All right, wonderful. The next question is about intercepts. What are the x-intercepts? Now, you're being asked for x-intercepts in the plural sense because there's more than one. For the x-intercepts, you're looking at places where your graph intersects the x-axis. So those places would be here. And run your pencil along the x-axis. There's one. And another one of them actually occurs at x equals 20. Now, some of you guys are thinking, the graph stops here at 20, 0, but it doesn't keep going. Is it really an intercept? Doesn't matter. Even if the graph just touches the axis and turns back around again, it's still considered to be an intercept. So we are going to include all three of these values as our x-intercepts. So one of them is -12. And we don't have special notation for this. We're just going to list them out. We have another one that we'll consider that 14 and between 12 and 16. And then the last one is 20. Now, sometimes you're going to be asked for your intercepts as ordered pairs. So make sure that you're paying attention to the directions. If you're just being asked for the value of the intercepts, this is how you're going to list it. If you're being asked to list them as ordered pairs, well, these are all ordered pairs for which the y value is 0 by very nature of the x-intercept. So you can also list them like this if you're asked to do so. And actually, I think your author asks for ordered pairs more often than not. So it's a good thing to stick to. Now, when you're being asked about the y-intercept, it's not asking you about possible y-intercepts in the plural. It's asking you for a singular value for the y-intercept. And that is because you've been given and you've been told that this is the graph of a function. A function cannot have more than one y-intercept. If that was the case, then that must mean that your graph goes through the y-axis on 2 different locations and it would fail the vertical line test. That's one way of thinking about it. So a function can have at most one y-intercept. So let's go ahead and list that out, that your y-intercept is the place where your graph crosses the y-axis. And we cross the y-axis right here at y equals -12. And that is your y-intercept. And we can list that as an ordered pair, 0, -12. And that is because to find the y-intercept, we let x be 0. We're sitting here at the origin and we move down 12 units to find it. So just be careful when you're listing these as ordered pairs. Your x-intercepts will always have 0 as the y-coordinate, and your y-intercept will always have 0 as the x-coordinate. Questions on D?
Yeah, I have one question. So for the x and y intercepts, why did you put them in parentheses instead of brackets?
Oh, because those are just points on a graph. Yeah, I can see the confusion because we've kind of been talking about lots of different types of notation and ways of looking at these things. The x and y intercepts, we're just looking at in ordered pairs just because they're points on the graph. So this point is -12, 0, or yeah, this one's 14, 0. That one's 20, 0. A lot of times that's how you're asked for intercepts.
So if they're just points on the graph, you use the parentheses.
Mm-hmm.
Okay.
Yes, you'll write those as ordered pairs. So you kind of have to just pay attention also to your input instructions. If I asked you on a test, find the x-intercepts, if I stated write them as ordered pairs, I would expect you to write them like this. But if I didn't add that instruction and I just said find the x-intercepts, this would be acceptable. And let's say you answered this and you didn't write them as ordered pairs, I would still give you some points because you still found them. You still knew what an x-intercept was, which is really what I'm testing you on. But then you would lose probably a point for not putting them in the form that I asked for. So yeah, now that you've asked that question, I can see that there was a lot going on with this. So the answer for A is just a number. You'll be given f of 16 equals, and then you just find the number. For B, we use two different types of notation, and we were talking about a range of values between this number and that number. For C, when we were talking about the domain and range, again, we were talking about a range of values. With the domain, it's still a range of values as you go from one value to the next. Whereas with the x and y intercepts, you're looking at just point values, individual points. Does that help? Okay, all right, I'm glad you asked. Any other questions here? I thought I saw Jasmine on mute. Did you have a question, Jasmine? I can't see her.
No questions.
Oh, okay. Just making sure. Wonderful. All right. So we're going to do something similar, just on a smaller scale, using a different graph. We're going to use the graph to determine the function's domain and range. Now, I would like for you to put a little arrow on the end of this to indicate that this direction continues. If I were to give you something like this on a test, I would have put the arrow on there. I just forgot to include it on here, and I don't want it to look confusing. So this is very different from the graph that we saw in the previous example. I don't know if I can, no, if I make this bigger, it does not. I would have to expand it. That's okay. This one kind of just stops at the ends, whereas this one has a stopping point right here, and then it just keeps going up and to the right forever and ever and ever. So when we're listing the domain and range, same idea. For the domain, we're looking at the smallest possible value that x can take on. Remember, to look at the domain, we're thinking about going from left to right. So the leftmost point on the graph, and don't say 2 because 2 doesn't correspond to the x-axis, is 0. So we go from 0 all the way to the right. What do you guys think, square bracket or parenthesis? You can use the chat feature if you want to chime in. I haven't seen anyone chatting today. Square bracket or parenthesis?
Both.
Both. But what about on 0?
Square.
Parentheses.
Yes. So the answer both was not incorrect because this whole interval notation is going to need both. But on the first point, we're going to use a squared off bracket because we do have the point at x equals 0. So as we move from 0 to the right, we can be equal to 0. So we're going to use that. GN. All right, let's see. As we move to the right, we don't actually have a stopping point. The arrow is a big indicator here that it's just going to keep going. And it's just going to keep going in this direction, which means it can only keep going further to the right. How we denote that is to say that the graph goes off to infinity. And that looks like a sideways 8. And we can never equal infinity. Don't ever put a square bracket on infinity. Infinity always gets a parenthesis. I'm going to even note that. Infinity always gets a parenthesis. Never, never, never a squared bracket. Because you can never equal infinity. It's only a place that you can try to attain and you'll never get there. Okay, so remember your domain are values from left to right. Try to avoid thinking about this value as being a 2 because that has nothing to do with the x values. We're looking as the graph goes from x equals 0 all the way to x x approaches infinity. Any questions on the domain? Okay. Wonderful. For the range, we're going to look from bottom to top. I'm going to look at the smallest y value that occurs on the graph. And as you're doing that, you're going to go from bottom to top. The smallest y value we can possibly attain is 2. And for the same reason that we included 0 in the domain, we're going to include 2 in the range because we can attain the value of y equals 2. Now, I know that it just looks like, oh, this graph, you know, it's very slowly increasing. I'm sure it levels off somewhere. No, it's just going to keep going on and on and on and on and on, which means that even though it's going to be going upwards and upwards and upwards very slowly, it's still just going to keep going up. What that means is that you cannot actually find a maximum y value for this graph. We would say that the range is from 2 to infinity because the graph just keeps heading up and to the right as it moves its way out of our coordinate system. Questions on the range? Okay. Wonderful. We're going to use more of these topics in 2.2, which is called more on functions and their graphs. So we're going to do more of this. There's a little bit more definition in here. I find that sometimes the definitions in here trip people up a little bit, but that it's actually pretty intuitive to not have to use them. So I'm going to let you read this definition for identifying intervals on which a function increases or decreases or is constant. And I'm going to let you read the definition for using graphs to locate relative maxima or minima. And then we're just going to go through it, and we're not really going to be using this definition directly. So you read those, and then we'll answer these questions. I'm going to finish my attendance real quick. All right. Everyone's talking about Nancy's parrot now. Is it just chilling on your shoulder, or is it on some kind of perch? We can't tell. Oh, it's on a perch. Wonderful. How much did that bird cost? I have to ask.
600.
600? Almost as much as our dog. Yeah, I know. My husband's friend like drove to California to get this bird that he really wanted. It was like this obsession that he had. And then when he got there, they wouldn't let him get back on the plane with it because it was like this exotic animal. And I don't know if the paperwork wasn't filled out right. So he rented a car and drove it back home from California and then went to work the next day, like 3 hours later at 4 a.m. Crazy. So when I see parrots, I think of that guy, but very cool bird. Lovely bird. Oh, everyone wants, oh, sorry, not everyone. Ben wants you to teach your parrot the quadratic formula. You think that's a possibility? The Pythagorean theorem. I know. I was going to teach my son the quadratic formula. He's, you know, his brain is like a sponge, so even though he can't use it, he's 5. I just thought it'd be good if it was in his mind for down the road. He wouldn't have to, like, you know, those things from childhood really stick with you. Okay, wonderful. I got your attendance. 2.2, sorry. We have to move away from fun parrot talk to talk about functions. All right. We are going to identify the following for the graph, where the graph is increasing, decreasing, constant. Why am I doing this there? It does not work that way. And any numbers at which f has a relative maximum, what the maximum are, and where f has a relative minimum and where the minima occur. All right, so let's look at this here. I did something weird to my, to move this way. Okay, so the first part is number 1A, where the graph is increasing. Now, these are intervals. What I have found in the past is that students don't actually have a hard time finding values where the graph is increasing or decreasing. They just have a hard time learning how to write it mathematically. When you're talking about intervals where the graph is increasing or decreasing, you're going to be noting this in terms of x. So, for instance, go ahead and look at your graph and find intervals where it's increasing. Clearly, it's not the interval right here. Right here, the graph is going downward. As you move from left to right, the graph is going down. But once you hit this bottom point, which we'll talk about in a couple minutes, your graph starts to increase from here. It goes up. Now, this is the interval that we're looking for. We need to talk about the points x at which this increasing occurs. We're always thinking about these things as x values as we move from left to right. So where the graph is increasing, always including parentheses, not square brackets. Oh, you know, this show dog thing, you guys are really into the dog. Stick around for the office hour because I did show a picture of the dog on Monday, but everyone was in such a hurry to get out of here. I guess you weren't that interested. Stick around a couple minutes and we can do. Oh no, we don't have class Monday. Thanks for reminding me. It's an online class, so maybe you weren't sure, but yeah, we don't have class Monday because Monday's Labor Day. So don't log on Monday. This might be confusing though, because on your calendar invite, I forgot to exclude Monday. So if you accepted the calendar invite, then this class is on your calendar for Monday the 7th. But I will not be on. Don't log on. It's Labor Day. Okay, we're good on that. Excellent. Excellent. Okay. Wonderful. Let's get back to this graph. All right. So the values of x, again, I'm just going to put these on here and label this so that we know what's happening at these two places. The values of x for which your function is increasing are starting as soon as we get past x equals -2. Notice that at x equals -2, the graph isn't actually increasing. When x equals -2, that's where you hit this bottom point. At this point, the graph is neither increasing nor decreasing. But as soon as we move even a little tiny infinitesimal value to the right, so getting to be a little bit greater than -2, like -1.9999999, we're at a place where the graph is starting to increase. That's why we have to use a parenthesis instead of a bracket, because we cannot say that the graph is increasing when it's sitting here at this point, the point where it changes its course. So from x is -2, between that point and the point where x equals 0, which happens right here, we would say that the graph is increasing in this little stretch. So always looking at the x values, the graph is increasing from -2 to 0. Now we're going to use some more notation here, because we have more than one interval where the graph is increasing. So as we got to this point, we said, all right, the graph stopped increasing. We're done there. Heading down this way, definitely not increasing. We get to this bottom point, and then as soon as we leave here, the graph starts to increase again. So as we work our way from 2 up to 4, the graph is also increasing. When you're using interval notation, we use a symbol called a union to combine more than one interval. So on the interval from -2 to 0 and on the interval from 2 to 4, the function is increasing. This might seem weird at first. I know a lot of times it's really hard to ignore the y values. We're just listing x values. That's the way this is done. We're going to do this again for decreasing values. Before I do that, does anyone have a question on where the values are increasing or why we noted this the way we did?
So the last point doesn't have a bracket on it either?
Okay, great question. Yeah, so for the last value for 4, same idea here. We are increasing up until we get to 4. Now, technically, we don't really know what happens at 4, but because it stops, it can't be increasing. The graph stopped here, so it can't be increasing at that point. So we would still use that open parenthesis. Does that answer your question? It's a great question. This is a hard lesson to get through just because there's a lot of notation and a lot of little things that sometimes are hard to catch. Angel wants to know, why did we put 4? Well, the reason we use 4 is because 4 was the x value at which this graph stopped increasing. So we didn't want to say infinity because there was no arrow on here. Because it just stopped there, we don't know what happens after it goes past 4. We just know that up until it reaches 4, this x value of 4, that it continues to increase. Does that answer your question, Angel? Excellent. And you know what? I noticed that Mia also responded to his question on the chat. I don't mind that at all, because sometimes the way that I explain something, or maybe my understanding of your question, is not quite the same as the way you intended. So if somebody else can offer clarity that maybe I can't provide, I'm okay with that. I mean, a lot of times I'm in class and I'm teaching, and somebody will whisper to the person next to them and be like, why did she put 4 here? And then they'll answer back. And you don't really have that when you're in an online class. So don't ever feel like you're stepping on my toes. If you feel like you can answer someone's question, go ahead. I'll still address it because I don't want to leave you on your own. That's the whole reason why I'm here. But sometimes maybe I don't catch your question the same way. Let's do the same for decreasing. And then if you still had a lingering question on increasing, I think that will clear it up. So when we talk about places where the graph is decreasing, same idea here. We can look down towards the x-axis and we'll see that our decreasing starts as soon as we get past x equals -4. This function will start to decrease. So I'm moving my way from left to right. I'm starting out here at -4. I cannot include -4 because it's not actually decreasing at that point. We don't know what it's doing, but there's just a point that's sitting there. It's not decreasing until you get just to the right of that. And then all the way up from -4 to -2, the graph is decreasing. Remember, we're always looking at x values. We're always thinking from left to right. From -4 to -2, in this interval, the graph is decreasing. And because we know we have one more interval where the decreasing behavior is occurring, we're going to go ahead and join these two with a union symbol. We know the graph is also decreasing as we start from this point and go down. So again, you're looking at the x values. The x value at this point is 0. So moving from left to right, from 0 to 2, the graph is decreasing. So all the way from 0 to 2, the graph is heading downward. And we always use parentheses when we list intervals for where the function's increasing or decreasing. Any questions on A or B? Okay. C, where the graph is constant. We're looking for intervals where that occurs. You guys have not seen an example of this yet. We're going to do an example of a place where a graph is constant next. There aren't actually any places on this graph where the graph is constant. If you're thinking, well, what about at these points? That doesn't correspond to your definition. And sometimes when something's not clear, you have to look at the definition. A function is constant on an open interval I if f of x sub 1 is equal to f of x sub 2 for any x sub 1 and x sub 2 in the interval. What that means is that there have to be two distinct x values for which the y value stays the same. That's not happening here. You would be looking for a place where your graph looked like it had a horizontal line, and that doesn't occur here. So we would say that there would be, as far as what the intervals were, there would be none. And if you wanted further explanation, you could say there are no places on the graph with horizontal lines. And again, if that's not 100% clear, I'm going to go over an example of what a constant interval looks like on a function in just a minute. And then if you're still not sure, ask me after that. So we don't have any intervals where the graph is constant. Now we're looking at numbers, if any, at which f has a relative maximum. Now, this is kind of tricky too, and it's something that you have to go back to the definition for. A function value f of a is a relative maximum of f if there exists an open interval containing a, such that f of a is greater than f of x for all x not equal to a in the open interval. Now, an open interval means that you have to be able to look at a value from a certain point to the next. Clearly, looking at this graph, if you're looking for a maximum, you would probably point out this spot first. A maximum is always like when you get to the top of a mountain and you start to head back down again. So that change there where you change from increasing to decreasing would be a relative max. But in order to get that relative max, you have to have a point at which you change from increasing to decreasing. That happens here. Now, sometimes people look at these two values and say, well, these are some highest values on the graph. Why can't we include those as relative max values? The answer is because you don't have an open interval here. You don't have a situation where the graph went from increasing to decreasing. There's nothing to the left here. In order to be a relative max, there has to be a hill at which you are the top of. Over here, you don't have that situation. You just stop. And that means you don't have an open interval. And if there's no open interval, then you can't be a relative maximum. So this would be not a relative max. And for those of you taking calc, you're going to talk a lot about this later on down the road. So it's really important that we're able to find that spot where we change from increasing to decreasing in order to get a relative maximum. And that does not occur at these 2 points, even though they are the highest point in their region. So when we talk about numbers at which f has a relative maximum, we're looking for 2 different things. We're looking for an x value at which the maximum occurs first. So the numbers at which f has a relative max, we would say the relative max occurs at x equals 0. And this is a 2-parter. You're always going to be asked where the maximum occurs and then what is the maximum. So the maximum occurs at x equals 0, and the value of the maximum at this point is 6. Now, how MyMathLab will ask you this is it's probably going to say something like the maximum occurs at x equals blah, and then you'll fill it in, and then it will say something like the value of the relative maximum is, and that is the y value. So the value of the maximum is always going to be the y value at the maximum. Just how high does it go, basically. We can do the same thing for minimum. In this case, you're looking at this graph and seeing 2 places where there's a dip. So you're looking at that change where you went from decreasing to increasing. As long as it's occurring, you have an open interval at which this value is the smallest point. So this point will be a relative minimum, and this one will also be a relative minimum. You can have more than one on a graph. You can have an infinite number if you had some sort of cyclical graph like you'll see in trig. So you actually have 2 values here for the relative minimum. So when you list this out, you can just list it out twice. You can say x equals, and then this one is at x equals -2. That's the x value at which the minimum occurs. And then the min value is all the way down to -6. And then we would also say that the graph has a relative minimum when x equals 2, because when x equals 2, y hits another valley, which is also -6. Sorry, that looks a little bit messy. I need to move this thing because I don't have a lot of wrist space over here. Sometimes students wonder, well, what if this point was at -2, -7? Would this still be a relative minimum because it only goes down to -6? It still would be. Anywhere you see on your graph where you have some sort of valley that dips will be a relative minimum. As long as you see that there's a change in behavior from decreasing to increasing, that will be a relative minimum. Doesn't matter if it happens in a bunch of different places throughout the graph. Doesn't matter. All of those would be considered minimums as long as you have this cup behavior occurring. Same with the max. As long as you have this top of the hill, you can have more than one, and they can all have different y values. Before I move on, I want to make sure that there aren't any questions about the relative minimum or maximum points. By the way, maxima, minima are just plural for maximum, minimum. You'll see both of them used throughout. All right, so we were talking about these constant functions. And I really like this example. This one says to sketch a graph of a function that's constant in the interval from -3 to infinity, not including -3. So we're going to have to see what sort of behavior we can possibly have occurring at -3. But let's go ahead and make an example here. Now, there are an infinite number of ways to make this graph. And if you want to sketch one on your own, I can give you a minute to do that if you'd like. But I guess I haven't really shown you a constant. But go ahead, take like 30 seconds, jot something down, and then I'll put down an example that follows this criteria. But there are a lot of options here. So constant means it is neither increasing nor decreasing over an interval. So I'm going to sketch my graph. I'm going to put it at y equals probably 2, just to make it most clear. If I want it to be constant from -3 all the way up to infinity, I just need to have it look like this. Some sort of straight line. I did not use a straight edge, but that is a straight line. And then you could do anything you wanted to the left of -3. You could even put an open circle at -3 if you wanted to. But let's say I did something like this at -3. I mean, there are an infinite number of possibilities here. Nothing else matters on this graph except that on the interval from -3 to infinity, it's constant. That's it. So do whatever you want to the left of -3. And by the way, this did not have to sit at y equals 2. You could have put it down here. It could have been way up there. It could have been somewhere that's not even on your grid, although that would have been hard to graph out. I just put mine here because I thought it was the most logical place to put it. Any questions about this? I also want to note that I put the arrow on here indicating that this direction continues. So if you put like a dot here, that does not indicate that the graph is constant all the way off to infinity. So make sure you include that arrow so that it's very clear that your graph continues to head off in that direction at that constant value. Okay.
Could it be infinity both ways and still be constant?
Well, if you took it all the way to -infinity, then it would be constant for more than just this interval. I mean, technically, you could have made it do that, like to the left of this. You could have even done something like this, and it still would have followed this rule. But in order to technically follow this rule, you don't want it to be constant immediately to the left of -3. Does that make sense? Okay. But this would have been fine too. Okay. All right, the next thing we're going to do is, I always feel like it's one of the more challenging things in this chapter. Identifying even or odd functions. Now, when you're doing this graphically, it's not as bad, but when you're doing this algebraically, you have to be very, very careful with your signs. This will pop up again in calc. Most of the stuff you're seeing in this section, you're gonna see again in calc. It's all very much the underlying information that everything is dependent on as you're working your way through Calc 1. All right, but let's talk about even, odd, or neither functions. A function f is an even function if f of -x equals f of x for all x in the domain of f. That means that the y value is the same whether your x value is the negative of that value or the positive. So let's say x equals 3, x equals -3, the y value would be the same. So the y value at -3 would have to be equal to the y value at 3. So that would tell you that it's an even function. We're going to look at these graphically after we do the algebraic approach. The right side of an equation of an even function does not change if x is replaced with -x. So that means you can evaluate the function at -x and the right-hand side stays the same. That's how you know it's even. The graph of an even function in which f of -x equals f of x is symmetric with respect to the y-axis. A function f is an odd function if f of -x is equal to negative f of x for all x in the domain of f. Every term on the right side of the equation of an odd function changes its sign if x is replaced with -x. And the graph of an odd function is symmetric with respect to the origin. You know what? Let's do the graphs first, and then we'll come back to the algebra, because I think it'll give you a little bit more motivation to do the algebra if you at least kind of see what this means. So the graphs are on the next page. Okay, so this is the same information repeated from the prior page. The graph of an even function will be symmetric with respect to the y-axis. So we're going to look at these pictures for 5 through 8, and we're going to determine, is this function even, odd, or neither? Now, it's not going to be both. It's going to be even or odd, or it's going to be neither one. So for number 5, what you're looking at here is you're trying to determine whether you have y-axis symmetry or origin symmetry. Now, if you don't know what origin symmetry is, I'm going to write that down because that's a tough one. If a graph is symmetric with respect to the origin, that means you can flip the graph upside down and the graph looks exactly the same. That is origin symmetry. So sometimes you will be sitting there and you will literally just turn your paper upside down and see, does this graph look exactly the same? If it does, that's origin symmetry. We're looking at these visually. So for number 5, just visually, you're looking at this and you're trying to see if there's symmetry. Now, x-axis symmetry we don't care about. That has nothing to do with whether the function's even, odd, or neither. But y-axis symmetry is something that we're looking for here. And if we have y-axis symmetry, then we have an even function. Now, that is what we have for number 5. Notice that all of the points that are represented on the right for number 5 are also represented on the left. If you were to take this graph and flip it over the y-axis, you'd get the exact same picture. That's what you're looking for. Can I basically take this graph, fold it in half, and get the same exact points to copy over? That's y-axis symmetry. So we would say that this graph has y-axis symmetry. And you're not going to get anything super tricky where you're like, I don't know, it looks close, maybe it's not. Your examples here are going to be really straightforward. This is y-axis symmetry. You flip the graph over the y-axis and you get the exact same picture. Because we have y-axis symmetry, we would say that this is an even function. Now, does anyone have a question about number 5? Okay. Now, number 6. You definitely don't have an even function. You don't have y-axis symmetry. If you took this part of the graph and you flipped it over, if you were to have y-axis symmetry, you'd be seeing it up over here. We don't have that situation occurring. This is a situation where you could possibly have origin symmetry. However, note what's occurring in your graph. You have this graph actually having its little pivot point below the origin. If you were to flip this upside down, it almost looks the same. You still have a situation where as you head from left to right, the graph is increasing. However, now it's got its pivot above the origin. Doesn't look exactly the same. So this one increased from left to right. The pivot was above the origin. And for this one, it was increasing from left to right, but that pivot was below the origin. So we would say this is a situation where we have neither.
Could you go up a little bit? I think I've missed
sorry.
something. Okay, I'm good.
Okay. Now for number 7, you got it, Karen?
Yes, I got it.
Okay.
Thank you.
For number 7, this is one where it looks more like you've got a situation where you have origin symmetry. The reason being, all the action that's happening with this graph is happening on this x-axis. So if you take a good look at the function, it's increasing from left to right. Everything that's important is happening here at the x-axis. Get a good look at it and remember what it looks like. Then you flip it upside down and it looks like it's exactly the same picture. Because of that, we would say that this graph appears to have origin symmetry. And if our graph has origin symmetry, that means it's an odd function. And you can even just kind of, you know, get a few points on here. For instance, there's a point at 4, 2, and there's a point at -4, -2. Your definition for having an odd function, if you look back to the top, an odd function is one in which f of -x equals negative f of x. So like f of -4 is the same value as negative f of 4. So if you wanted to plot some points down and kind of test that out, you'd be able to see that too. I find that students are able to see it a little bit better visually just by flipping their graph. Any questions on number 7? Okay. Number 8. If you don't remember your quadrants, you've got quadrants 1, 2, 3, and 4. It looks like you've got part of your graph appearing in quadrant 1 and another part appearing in quadrant 3. It's definitely not even. You don't have y-axis symmetry. If you had y-axis symmetry, then all of these points over here would be occurring over here in quadrant 2. You don't have that. But flip it upside down and notice that you have the same exact picture where you have a graph occurring in quadrants 1 and quadrant 3. So this is another situation where you have origin symmetry and an odd function. So if you're given a graph, you're just going to be looking at the values in your graph or looking at the behavior of the graph and determining whether your function is even, odd, or neither, and being able to answer questions about the type of symmetry that it has, if any. Now I want to talk about how to figure out whether your function has these symmetric properties using algebra. Before I do that, does anybody have a question on the graphs? Okay. Okay. Then let's go back to number 2. We're going to do this straight from the definition. We are going to determine algebraically whether the function's even, odd, or neither. What we're looking for here is if we find f of negative x, is it going to be equal to f of x? Is it going to be equal to negative f of x? Or is it going to be neither? So if we find f of negative x and we find that it's the same exact function, then we'll say that our function's even. If we look at f of negative x and find that it's the opposite of our original function, then we'll say that our original function must be odd. If it's neither one, then we get a neither. So let's go ahead. First, I'm just gonna write this down too because I think it's important. Start by finding f of negative x. If f of negative x equals f of x, then your function is even. If not, find negative f of x. If f of negative x equals negative f of x, then your function is odd. If f of negative x, sorry, my f's are starting out as parentheses, does not equal negative f of x and it does not equal f of x, then you have a neither situation. So this is your procedure. I wonder if some of you guys are wondering, can't I just graph this and look at it visually? I mean, technically on your homework, I can't stop you from doing that, but on your test, I'm going to tell you when I want you to do this algebraically, and I'm going to make you do that at least once. Probably not more than twice, but this is a really important skill that you need to have down pat. So yes, technically on the homework, you can do that. I wouldn't recommend it because you need the practice. All right, so number 2, f of x equals negative 5x cubed. I'm going to start by finding f of negative x. Now what that means is everywhere I see x, I'm going to swap it out with negative x. And when you do that, you're going to have to use parentheses here and be very careful with your order of operations. This negative sign in front of the 5 stays right where it is. The only thing I'm going to do is switch out x cubed with negative x cubed. Oh my gosh. Sorry, guys. I don't know. The dog is too much. All right, now I want you to simplify negative x cubed. And in order to do that, you need to think about what happens when you cube a negative value. So negative x times negative x times negative x. That's 3 negatives. If you'd like, write it out if you find that helpful. This is really just negative x times negative x times negative x. Now, we kind of talked about this Monday when we were talking about using the quadratic formula, but we were talking about how we can add up our negative signs, and if we have an even number of them, then they'll turn positive. You can do the same thing here. I have a negative 5 times a negative x. Well, both of these together will give me a positive quantity. then these two negatives together will be multiplied together to make a positive quantity. So what I end up with here is an answer for this expression that's positive. The sign is positive on it because I have 4 negative signs. An even number of negative signs makes a positive value. And then x times x times x is x cubed. Now, we started out by finding f of negative x, which ended up being 5x cubed. That is not the same as negative 5x cubed. So f of negative x does not equal f of x. Sorry, I'm going to box this off a little bit. So we don't have an even function. That's our conclusion here. Now, just because it's not even doesn't mean that we should stop. We still need to determine whether the function is odd. Before I do that, I'm anticipating that you might have questions here. Please let me know if you have a question so far. Unfortunately, this is one of those very subtle things that I do where when you do it on your own, it's like, wait, what happened? What? But it makes sense when you look at what I do. It's all very subtle, but if you think of anything, pop up and ask me a question. All right, so your instructions were start by finding f of negative x. If f of negative x equals f of x, your function's even, and then you stop. If it's not, find negative f of x. Now, negative f of x is not the same as f of negative x. Negative f of x takes your whole function f of x and makes it negative. So what that means is you're taking a negative of your original function f of x, which was negative 5x cubed. So negative f of x equals negative 5x cubed. Now you have 2 negative signs. And if you have 2 negative signs, that makes a positive. So a negative times a negative is a positive. And negative f of x is positive 5x cubed. So then you will go back to your directions. If f of negative x equals negative f of x, then your function is odd. Well, we found that f of negative x was 5x cubed. We also found that negative f of x was 5x cubed. We now have evidence that our function is odd because we have f of negative x equals negative f of x. So we can say that f of x is odd. Okay. Now, if you weren't sure about your work algebraically and you thought it was right but weren't totally positive, feel free to pop this into your graphing calculator and verify that when you graph negative 5x cubed, you get a picture where you flip it upside down and you get the same exact values to pop up. Feel free to check this by graphing. I think it's always good to be able to see things using different methods. Questions on number 2? Number 3. This one has 2 terms. Always start by finding f of negative x. So we're going to do that first. F of negative x is negative 3 times negative x to the 4th minus negative x squared. Now, if you would like to write out negative x times negative x times negative x times negative x, if you find that helpful, feel free to do that. I'm not going to keep doing that because we can just look at the exponent that's on this particular factor. If you take a negative value to an even power, it's going to come out positive. Just like if you take a negative number and you square it, it comes out positive. When you take it to the fourth, you're just squaring it twice. So in this case, we can say that this expression is the same as -3 times x to the fourth. I put in parentheses there, but don't get tripped up on the parentheses. They're not needed. I just put them in on a whim. And then be very careful here. Do not multiply these two negatives together. That's something that students do that leads them down the wrong path. Remember your order of operations. You must have parentheses here, and you have to apply the exponent before you multiply. So make sure that you're simplifying this exponent first. Don't multiply these two negatives together. So you have a negative, and then negative x times negative x is positive x squared. Negative x times negative x is just x squared. Now, I put parentheses on it. If you want to take them off, be my guest, and you end up with f of x. And you know what, just to make this match, if I was going to put parentheses around the first term, I should have made it match in the second term. So I'm just moving that parenthesis over. Again, they're non-essential. I just wanted to make sure it was matching. F of negative x is equal to f of x. That means that your function is even. When you swapped out x with negative x, you simplified, you ended up with f of x again. Questions on number 3?
Yeah, I was gonna ask, does it matter if the exponents are in or out of the parentheses? Because you have them like both.
Yeah, I mean, it makes a big difference. In these two cases, it doesn't matter because they're both positive values. So whether they're squared or taken to the fourth for a positive, it doesn't matter. But if I had the parenthesis moved here, yeah, it would make a big difference because that would be negative x to the fourth instead of negative x to the fourth. Yeah, it makes a big difference. I'm really glad you asked that. Remember that if you take negative x and you square it, that negative also gets squared. But if you take a negative x squared, you just get negative x squared. Does that clear it up, Josh?
Yeah, it does.
Okay. Did anyone else have a question on number 3 or the parentheses or anything? And like I said, you could have left this without parentheses on this line. Not this line. The first one had to have them, but the second line you could have left them out and that would have meant the same thing. Okay. So let's do number 4. F of x equals 9x cubed plus 3. The first thing we're going to do is find f of negative x. So that's 9 times negative x cubed plus 3. So just swap out your x with negative x. And now you're going to think again about what it means to have a negative value and have it cubed. So if you have a negative cubed, that means you have 3 negatives, and an odd number of negatives will stay negative. So if the odd number of negatives stays negative, then you end up with just a negative 9x cubed, and then the plus 3 didn't change. I feel like I might need one more line on there to clear up any middle confusion there might have been. If you feel comfortable going from here to here, that's great. If you don't, I'll add in some extra stuff here. This is just negative x times negative x times negative x, and the intermediate step. And then these two negatives, or those two, whichever two you want to combine, two of these will come together to make a positive, and you're going to have one left over. So that one left over will just hang out in the front. So you could, if you wanted to, rewrite it like this. And then you could just move that negative in front of the 9, and you'd be saying the same thing. Now, f of negative x does not equal f of x. When that happens, we have some guidelines. If f of negative x equals f of x, it's even. If not, find negative f of x. Okay, so that'll be our next thing that we're going to do. We're going to look for negative f of x. Negative f of x, I'm just going to take a negative of my original function. So that whole function, I'm going to apply a negative sign to it, and I'm going to distribute it into the expression. So the whole thing gets negative, not just the first term. So we have negative 9x cubed minus 3. Don't forget to distribute that negative sign to both terms. Now the whole point of doing this, someone has a question, 1 second. If f of negative x equals negative f of x, your function's odd. However, we had a situation where f of negative x does not equal negative f of x, because our f of negative x was negative 9x cubed plus 3. We don't have that. So it's not even, and it's not odd. It's neither. Someone had a question. Who was it? I don't know. Someone came off mute. That's all I know. So I assume they had a question. I'm like totally pitch black now. I can't even see myself. I gotta fix the lighting in here. Can you guys see my presentation okay? If you cannot, tell me, because it's a little dark on my screen. But I mean, it looks fine on the computer, but on the Google, you can see it. Okay, good, wonderful. Because I don't watch the videos after I post them to YouTube. Ugh, I don't think anyone does that. Okay. Questions on number 4? My advice to you here is look through this example, keep it by you while you're doing your homework, follow it closely. I really tried to put some good notation on here just so that it would be easy to follow and you knew exactly what was going on. So hopefully you find that it is helpful. Okay. Did someone have a question?
I got a quick question.
Tell me, Ben.
Can I just see F at the top of the page? I stepped out of the room for that part. I think I know how to do it. I just want to see what it looks like to make sure I got it right.
Wait, what did you want? Oh, the
Can I
function.
see F? Yeah, the function.
Oh, you know, as long as your function looks like this to the right of -3, that's all that matters. Whatever's to the left
Okay.
is up to you. You do whatever you want with it.
Okay, cool. Thank you.
You're welcome. Okay, what else is left here? Because we only have like 4 minutes left, and clearly I can't finish this. By the way, I was looking at 2.4 today, and I did send you guys notes for 2.4, but oh, we just have like 1 page left. I don't know. Oh no, 2 pages left. Yeah. So I don't know. I sent you guys notes for 2.4, but it's a lot of review, and it's not stuff that you're really going to be seeing later. So it's something that I actually think it's an optional section. We're a little bit behind. I don't know why. It seems like an online class should go faster, but maybe it goes slower because there's a little bit less of me seeing you, and I don't know. Anyway, we're slightly behind. So I'm probably going to skip over 2.4 because 2.5 is actually important. 2.4 is like, you probably won't use it again the rest of the semester. And I think it's an optional section anyway from algebra. So let's stop here because I really don't have time to go any further. So we're going to finish this next time, and then we'll work on 2.5. And then I hope, because I sent them to the copy shop for printing, that you will have your 2.6 notes. Actually, if you wouldn't mind, and I mean, I guess the whole class doesn't have to do it. If you get a packet of notes from the print shop in the mail, sorry, I'm like, you can't even see me now. I'm like creepy. If you get a copy of all the notes in the mail from ECC, if you could shoot me an email and let me know, that would be really helpful, just to know that it was sent out and that people are getting it. Because all I heard was like, okay, this works, we can do this for you, but there was no mention of here's when we're going to mail it out and here's when they should get it or anything like that. So I don't know. I'm hoping that you'll have the 2.6 notes by when we actually cover 2.6. But it's taking forever, and more than half of you probably don't have notes from the beginning of class anyway. I don't know how many of you have access to a printer, so I know it's really unfortunate, and I'm sorry that it's worked out like this. Clearly, it's like a kink that, you know, can't easily be worked out with these online classes. But they said they're going to do it. They said they were mailing it out next week, and that was last week, so I don't know what that means. So if you could just shoot me an email and say, hey, I got my notes from 2.6 through chapter 8, just letting you know, that would be awesome. And then if I get that first email, I'll probably send an email to the class saying, people are starting to get their notes, just so you know, let me know if you didn't get them. And then maybe I'll do another one of those late night post office runs if it's only like 1 or 2 people, if you don't have access to a printer. Okay, I'm going to put up some homework from the rest of 2.1 and whatever we covered in 2.2. It'll be due Monday. We will have a quick quiz on Monday, and it will be in D2L. I'm going to send you some instructions on Monday afternoon, probably when I have it all totally ready for you and good to go.
Don't have class on Monday.
I thought we didn't have
Labor Day.
Oh my gosh, you're right. I'm like a robot over here. Monday, Wednesday. We don't have class Monday, so never mind. No quiz, because I don't want to start doing quizzes on Wednesday and then everyone's going to be like, wait, I thought you said quizzes were Monday. Do we have a quiz Wednesday? What's going on? Don't worry about it. Whatever homework is normally due on Monday, I originally, when I assigned it to you on Monday, I set the due date to the 9th, which is Wednesday. So we normally won't have homework due Wednesday, but I didn't want to have the due date be like 2 weeks out, and plus then you could get really far behind. So your due date for whatever homework I assigned Monday and today is Wednesday the 9th. And then forget about the quiz for next week. We'll do one the week after. We've got some time, no big deal. Okay, is that good? We're good now? No confusion? Okay, I will be here in the office hour for another like 17 minutes if you have questions. Will it be emailed? Sebastian, what do you mean? Will the notes be emailed? Oh, all the notes are on D2L. If you wanted to print out your own, all of them are there through chapter 8. So no, they won't be emailed, but they're on D2L. If you have trouble finding them, let me know. But they're under content guided notes. Have a wonderful weekend, you guys. Stick around for the office hour if you have questions about anything. Have a good weekend.